In this video, we will be deriving the simple harmonic motion equation. Now let's consider the following circular motion. What can we deduct from this? Well, actually, when viewed from the side, it looks like a simple harmonic motion, which looks something like this. And why is that? Well, when the x position is isolated, and the y position is also isolated, and we create a sort of graph, the position versus time graph, the object will actually move in a motion similar to something like this, as well as the y position. Okay, so what about it? Well, if we were supposed to place that into a graph, it would actually slow down over here and clump up over the peaks of the graph, causing it to look like a simple harmonic motion graph. Okay, let me give you a better example of this. So let's dissect this position. So what can we identify on this diagram? Well, we can see that this is the radius, and we can see that this is the x position of the object as well as the y position of the object. However, we can also find that there is an angle here, or as we call it, the theta. Now, let's really list down what we're given here. So we're given the x position, which is the position of the object in the x-axis, and we're given the radius, which is just the radius of the circular motion, and we're also given the angular displacement, which is represented by theta. So what about this is important in our derivation formula? Well, in trigonometry, we're given this equation. Cosine of theta is equal to adjacent divided by hypotenuse. And if we were to insert the current variables into this equation, we would have the adjacent be the x position, and the hypotenuse would be the radius. Okay, so from this equation, we can actually convert it into x is equal to radius times cosine of theta, sorry. And this will be very important for deriving the equation. Now, our objective is to derive the simple harmonic motion equation, right? Well, we can do so. If we want to do so, we need to figure out the time. Well, let's consider the following. Omega, or angular frequency, is equal to change in angle divided by change in time. Change in angle simply means the final angle is subtracted by the initial angle, and the change in time is basically the final time. Oh, sorry, this should be minus the initial time. If we were to use circular motion, then that means the initial angle would be 0 as well as the initial time. And if we were to insert that into this equation, it would be final angle minus 0, or we actually can just change that into theta minus 0 divided by time minus 0, which is equal to theta divided by time. Now, what can we use for this? Well, notice how this equation has theta on it, and we can actually replace that here. Okay, let's see. The omega is equal to angle divided by time, which we can change into theta is equal to omega times time. So let's just insert that into this equation. Omega times time. Okay, Cool, so we have this. Our objective here is to actually convert the angular frequency and change it into something else. So let's see what we can do. One full turn or one full cycle of the circular motion would actually equate to 2 pi radians, which is just a given formula. So we can change this into 2 pi divided by change in time. However, we can also change the change in time into something else, 1 period. And 1 period is represented by the symbol t. Therefore, 2 pi divided by t. So in simple harmonic motion, we are also given that the frequency is 1 per time. 1 per period, sorry. And therefore, this is just 2 pi times 1 per time, which is equal to 2 pi times frequency, since we're applying it into simple harmonic motion. So from that, we can change this into 2 pi frequency times time. Okay, let's consider this. At position 0, if we were to insert the previous equation, if the time was at 0, then the r cosine would be 2 pi frequency times 0. And so we can just cross this out into 0, and it'll become x time at 0, r cosine 0. If you remember, r cosine 0 is equal to 1, therefore it's just r. And r is actually equal to amplitude. This is because when you draw a graph here, a simple harmonic motion graph, and you notice this is the amplitude, it actually has the same definition as the r, because if we were to move this part here, it would actually equal to a circle. My physics teacher told me this a few days ago, and I thought it was an interesting pattern to notice since this is also r. Okay, so x is equal to amplitude times cosine 2 pi frequency times t. And that is our final derivation from the formula. However, we can also express it in another equation, which is not too different actually. However, in this one we use sine. Now, we still have to modify this equation a bit because sine is not equal to cosine. However, it's just a cosine graph but moved slightly. Therefore, we need to add it by pi per 2. And so these two are our final derivation. Thank you for watching. I hope you learned.